It's nice to have you all. So today we are going to continue with our discussion of regression analysis. Okay. Last time we had this assignment for you to go and do a scatter plot and to identify the tendency, whether the relationship between two variables, the dependent variable and the independent variable, whether the relationship is negative or positive. If you look at your scatter plot and there's a tendency for a downward slope line in the middle of the scatter plot, then there's a negative relationship. If there is an upward sloping line in the middle of the scatter plot, then there's a positive relationship. If the line is flat, then there is no relationship. So today we're going to now actually look at numbers and use those numbers to identify the nature of the relationship, positive or negative, and then the magnitude of the relationship, which could be anything from a negative infinity to a positive infinity. But let us just look at something more realistic. Maybe the slope shows that for every time that the independent variable increases by 1, then the dependent variable might increase by 5. So by plus 5, that means there's a positive relationship. If the independent variable increases or changes by 1, then the dependent variable will change by a minus 5, which is negative, or a plus 5, which is positive, or maybe it will change by a fraction or a magnitude that's bigger than 5. It can be any magnitude, positive or negative. So we're going to look at how to estimate the relationship between dependent and an independent variable. And then we're going to also test the hypothesis, whether the estimate that we obtain is really just a spurious number. If it is a spurious number, then your hypothesis test will simply show that the slope is 0. That means that the line that you're actually looking at is going to be a flat line. If the relationship is not spurious, that is, if there's a significant effect, if the independent variable has a significant effect on the dependent variable, then your null hypothesis will show that B is not 0, that the slope is not equal to 0. And we're going to go through that. Okay, so let me pull up some information here. Let us see. Okay, let's see. Okay, can you see my screen now?
Yes,
Hello,
Professor.
guys. All right. Okay, so sorry, I accidentally closed all my files, so I had to start looking for them again. Okay, so we're gonna do today, as I said earlier, what you're gonna do is a simple linear regression. We're gonna go from simple linear regression, and by this time next week, we're gonna be doing multiple linear regression, and we'll take it from there. Okay, but today we're going to go beyond just looking at a scatter diagram. Okay, we're going to now go and estimate a simple line. And so, but let us go back and refresh exactly what we are trying to do. Okay, the learning objective is to apply regression analysis to estimate the linear relationship between two variables. Okay, and also to evaluate the significance of the slope. Because like I said, whatever you do, you will always get some kind of a number. The question is whether that number is meaningful, whether it does indicate a true relationship, whether there's a relationship at all between two independent variables. So that is what we mean by evaluating the significance. When we evaluate the significance, then we're going to ask ourselves whether the slope that we have is a zero slope, or if it is a slope that's significantly negative or significantly positive. And then we're also going to evaluate a regression equation for its ability to predict using the standard estimate of the error, and also to estimate the coefficient of determination. The coefficient of determination essentially is a measure of how strong is the relationship. How strong is the relationship? How do you measure how strong a relationship is between a dependent variable and an independent variable? We use the coefficient of determination r to the power 2. And what that simply means is if you look at changes in the independent variable, okay, what percentage of the changes in the dependent variable can be explained by changes in the independent variable? And I put it this way. Suppose you think about the family expenditure on food, or let us say the family expenditure on clothing, okay? The family expenditure on clothing. Family expenditure on clothing depends on the income of the family, okay? So expenditure on clothing is the dependent variable that depends on the income. And income here is the independent variable. So as income increases by, say, $1, what percentage of it is spent on clothing? And so the question you ask yourself is, what percentage of changes in clothing expenditure is explained by changes in income? All right? It could be 50%, it could be 70%, it could be 80%, it could be 90%, okay? Now, that does not mean that if your income increases by 1, you're going to increase your expenditure on clothing by 90%. No, that's not what it means. It just means that if you want to ask yourself, what is it that makes a person spend money on clothing? Is it because their income is going up, or are there other factors? Okay. Now, so you can use that to explain changes in prices. For example, if the price of beef goes up by $1, the quantity demanded of beef will go down, okay? It might go down by 5 cents. But that decline of 5 cents, what percentage of it is explained by a change in the price? All right? Because if for example, the price of beef goes up by $1 per pound, and you decrease your purchase of beef, your expenditure on beef, okay? Is it mostly explained by that price? Maybe not. Maybe only 10% of it is explained by price, even though your expenditure might decrease by 50%. It might just be that you say, look, if beef is going to cost me this extra $1 per pound, I might as well not eat beef. Okay? Or it could be that you think that spending your money on something else is better than spending it on beef. So it could be a change in taste. It could be a totally different thing. It could be that at the point where the event occurs, which is a change in the price of beef, that you really have had your fill of beef. Okay? So we're going to explain that today. All right. So our objectives today is we look at the dependent variable, we look at the independent variable. What is the nature, negative or positive? What is the size or the magnitude? And how strong, what percentage of changes in dependent variable is explained by changes in the independent variable? And we measure that by using the coefficient of determination, which is r to the power 2. All right. That when we began to study regression analysis, we looked at what we are doing, which is we use an equation, y, the dependent variable, is equal to a, the constant value, and b, the slope, times the size of the independent variable, okay? And a is a constant, b is slope or the rate of change of y when x changes by 1, y changes by b, whatever b is. B could be a fraction, could be a whole number, could be a big whole number, it could be a small whole number. It could be positive, it could be negative. For example, this is an example of a positive relationship. Y is equal to 10 plus 5x, okay? In that case, x is the dependent variable, 5 is the slope, and 10 is the constant. So if x is equal to 3, y is equal to 25. That is 10 plus 5 times 3. 5 times 3 is 15, which is 25. Okay? If the relationship is negative, for example, y is equal to 25 minus 2x, then if x is 3, then y is 25 minus 2 times 3, which is 19. This is the kind of thing we're going to be doing. Now, in regression analysis, what you do is you estimate A and you estimate B. An estimate, okay? All right. So we go again, this is the equation. When we do an estimate, when you say something is an estimate, then there is a room for error. So this is why the equation is y is equal to a plus bx plus e, the error there. All right. We estimate A using A hat. We estimate B using B hat. This is what I was talking about. This is a scatter plot that gives you an idea of the tendency, the relationship, okay? If you make many calls, you will sell many copiers, and so the slope is positive. And our objective is to draw a line smack in the middle of the scatter diagram. Just like this one, you can see your objective is to draw a line in the middle of that scatter diagram. Okay, now we're going to use a formula called the ordinary least squares formula, all right? And I'm going to do an illustration so that you can see where we're coming from. The formula for ordinary least squares is b hat is equal to summation x minus x bar times y minus y bar divided by the summation x minus x bar squared, okay? So you see a bunch of numbers here. The question is, how do we get those numbers? Okay. So we're going to get some numbers. I'm going to use an illustration here. This is sales and sales calls. And so let me see if I'm going to get those particular. I'm going to use another illustration. It really doesn't matter, but you're going to probably see all right, so I'm going to stop share of this, and I pull up the data that we are looking at. All right, and I'm going to go through it step by step so that you can see what we're doing. All right, so this is the data on sales calls, okay? And mark the formula. Remember the formula that I put up there, okay? Don't forget the formula. Okay. Do not forget the formula. All right, so I'm going to bring up the formula. I'm going to stop share and show you the formula once more. Okay, so my suggestion is for you to write it down so that when we're walking through it, you will not have any difficulties. All right, do you see the formula? Hello? Yep. Okay, so you see the formula, okay? We're gonna try to derive these same numbers that you see.
Where it says model equation, is that what you're talking about?
What I have highlighted here, the formula for estimating B hat.
Summation, right. Mm-hmm.
Okay, and the formula for estimating A hat, all right? Okay, so write it down so that what I'm gonna, for example, if you look at the formula, you're gonna see the summation x minus x bar times y minus y bar divided by the summation x minus x bar squared. So the question you ask yourself, how do you get the summation x minus x bar and the summation y minus y bar? Okay, and then you multiply them. Okay, so how do you get that number? All right, and then the formula for A hat is y bar minus B hat times x bar. That is the formula for A hat. All right. And so the question then is, how do you get these numbers? Okay. You already see the formula for getting B hat. What is x bar? X bar is the mean of x. Y bar is the mean of y. And so write down the formulas and we're going to proceed. And then we're going to come back to this particular okay, so this is, and I'm going to take all of this out for now so that you don't see anything. All right, so you can see you get sales. Sales is Y, and sale calls is X. The more calls you make, the more sales you make. Now, that makes a lot of common sense, all right? If you're a salesperson and you just sit on your desk, you might still make sales. What's going to happen is that customers will call you and say, do you have so-and-so product? Yes. Can I come in to the car dealership or to whatever and look at some things? You say yes. And you just sit there and the business is coming to you. But somebody who is picking up phones and calling, depending on the kind of product, okay? Depending on the kind of product. Okay. And so I'm going to take that out too. All right. All right. So first of all, you calculate Y bar. Okay. You're looking at the formula, the things you need to calculate, X bar and Y bar. Okay. And then you're going to calculate B hat out of it. But first of all, to calculate B hat, you need X bar and Y bar, which is the mean of X and the mean of Y. And so that's equal average, and you pick it up there. And the average is 45. Okay, the same thing you do for X bar, and the average is 96. And so here, now you begin to calculate Y minus Y bar, which is you take every value of Y and subtract it from Y bar. And that is easy to do. It's equal to C5 minus $C $20, which is you fix the 45, and so you get -4, and you drag it down. All right. Now, if you take the sum of Y minus Y bar, if you take the sum of any value from the mean of a set, the sum here is going to be 0. Okay. And so here you do the same thing. It's equal to D5 minus $D $20. Okay. Okay. And you drag it down to the end, and the sum must always be 0. All right. So now what happens next is you take Y minus Y bar squared, and you also calculate X minus X bar squared, which is you need X minus X bar squared. You also need Y minus Y bar times X minus X bar. So but let us do Y minus Y bar squared. So you take every Y minus Y bar, that is every Y deviation from the mean, and you square it, multiply by itself. So that will be equal E5 to the power 2. All right. And so we're going to need that. This is why I'm doing it. All right. We're going to need it. You do the same for X minus X bar, will be equal F5 to the power 2. Okay. You drag it down. All right. And then you also multiply Y minus Y bar times X minus X bar. So that will be equals G5 times H5. You multiply, you drag it down, and so this is what you get. To be sure that it was G5. No, it's E5 times F5, sorry.
I was about to ask that, Professor.
Well, you should have asked that. And you would have got a lot of credit. Okay. All right. So now you write down these summations, okay? For the purposes of your homework assignment, write down the summations, okay? So summation x minus x bar times y minus y bar is 6672. Summation x squared, x minus x bar squared is 25600. And summation y minus y bar squared is 2326. Okay. And so I'm going to now go back and plug in the formulas. You will see how the formulas plug in. Okay. All right. So you can see that these numbers are the numbers that we just did on the spreadsheet. Y bar is 45, X bar is 96. The summation X minus X bar times Y minus Y bar is 6672. And that one is 25600. Summation Y minus Y bar squared is 2326. So when you use that to calculate B hat, you get 0.2606. And when you use the formula for A hat, which is Y bar, which is 45, minus B hat, 0.2606 times X bar, which is 96, what you get is 19.98. Okay, so now you have 19.98, so, and 0.2606, you have an equation. You now have an equation that says that the number of sales you make, if you make absolutely no call, that is, if this X is 0, it will be $19.98 thousand or 19.98 units. Okay, we don't know how that is measured. What is being measured? It could be thousands of dollars. It could be number of units. Okay, so you sell almost 20 units per week, per month, whatever. If you do nothing, just sit there. Okay, but for each sales call you make, you're gonna get 0.26 more. Could be 0.26 of 1,000, which is another $260. It could be 0.26 of a unit. So there, you're looking at chancy outputs. But nevertheless, it simply says that the rate of change is 0.2606. If sales call increases by 1, the salesperson sales will increase by 0.26. About 4 sales calls will bag 1 additional sale. So, okay. This is what that means. Okay, if you are persistent and you make, chances are by the time you make 4 sales calls, you're gonna have 1 additional sale. Okay, all right. And so now, yes.
Quick question.
Yes.
So you don't want us to use Excel's function to calculate the equation. You want us to do this.
I'd like for you to do this, at least do one by hand.
Okay.
Okay, you have 2 problems, one for last week and one for this week. Try to do at least one by hand. I'll look for it. Okay?
Okay.
All right. So now the next thing is, how strong is the relationship? Okay? And we have R squared, the coefficient of determination, is B hat times summation X minus X bar, Y minus Y bar, divided by summation Y minus Y bar squared. Okay? And so that gives you the coefficient of determination, which is very easy. You already have all the numbers. So it's 0.2602 times 6672 over 2326, which is 0.746. And so now it means that 74% of changes of changes in the dependent variable can be explained by changes in the independent variable. So in a sense that for a salesperson's performance can be explained by the number of calls they make, but the number of calls explains only 75% of it. What is the remaining 24% or 25%? Can somebody give me an idea? If you're a salesperson and the number of sales calls you make explains how much sales you make, but only 75% of your success can be explained by the number of calls. What else could have been the remaining 25%? Can somebody tell me?
The people wanting to make it or like have the sale or like they're going out to go get it.
Who
The
are the people?
natural,
I'm going to come to you. Somebody says the people. Who are the people?
So like the people that are the consumers. I would
Okay, the
say.
buyers.
Yes.
Okay. If I mean, you could call somebody who really doesn't want to buy anything and say goodbye. Okay. What other factors? There, somebody was saying something.
I was gonna say the natural demand of the product.
Well, I mean that's especially if the people want it. The level of demand, of course, that's but you can take that for the individual. What other factors? A salesperson, and you're making calls.
Other variables like the amount of days you work, the amount of
Well, I
hours you
mean,
work.
the number of days you work, that will explain rather the number of calls you can make. But if you are making calls and you're trying to sell something to people, besides whether you are lucky enough to call somebody that really wants the product, what other factors explain that 25%?
Maybe experience, personality, like some people.
Experience, personality, the personality of the salesperson. If you're somebody who knows how to sweet talk, have you ever gone for your career preparation and what have you, and they tell you about soft skills?
Yep.
That's correct. Your soft skills, your ability to get somebody to pay attention to you, right? Okay. Your ability to persuade somebody. What if you call somebody that says, really, I don't care for this, and I don't know about it. I need more explanation. Okay. So this is how you plug in the formula, and it says that only 74.6% of your success depends on, explains how much you can sell. Okay. And so the coefficient of determination is 74.6%. And so we take it from there. All right.
Does it show R2 because it's supposed to be like the same thing as squaring the correlation coefficient? Is that why it says R2?
Yeah, that is R2.
Okay, that's what that. Okay, got it.
Yes, but your coefficient of determination is something that only addresses two variables at a time. Okay. If you have multiple variables, we have totally different measures. But we also use R2 if we have multiple independent variables. But we'll get to that. Okay. All right. So now the next thing is for us to ask ourselves to test the hypothesis whether actually calls explain sales. Okay. If you take any two variables and try to estimate a slope between them, or even an R squared between them, or an R, okay, the coefficient of correlation or the coefficient of determination, you will definitely get some number. But it might actually just be a spurious number, what we call spurious, which means just because you have two numbers, you're going to get another number. It doesn't mean anything. It doesn't mean that there's a significant correlation or significant relationship between them. Okay. And so if you think about the equation, y is equal to a plus bx, let's go back to it. Okay. Think about that equation. Our objective is to test whether this B is really equal to 0, statistically speaking. That is our objective. We want to ask ourselves, is B really equal to 0, or is B really a positive or a negative number that is significant? So that is the hypothesis we're going to test. Okay? So, and then we can use the model that we estimated and ask ourselves, if somebody makes 30 calls, if somebody makes 20 calls, if somebody makes 50 calls, what is the estimate of the sales that they will make? Okay, and so we can plug in 19.98 plus 0.2606 times 30, and that should give us about 27 to 28 sales. That is what we're talking about here. Okay, we already have that. And coefficient of determination, we are trying to estimate, okay? Oh, we've already estimated the coefficient of determination. We are trying to test our hypothesis whether B is 0. And so we use, we take the normal steps, okay? The null hypothesis is that B is equal to 0. That is, sales calls do not significantly affect sales performance. The alternative hypothesis is that B is not equal to 0. That is to say, the slope is not equal to 0. So we say that sales calls significantly affect sales performance. And so our step would be then to estimate B hat. We already have an estimate, and to calculate the standard error of B hat. Okay? The standard error of B hat, just like we calculate the standard error of the sampling mean of X. We estimate the standard error of B hat. And so we use a Z. We also state a level of significance. So let me say, state a level of significance. Okay, for example, (2.5%). Okay, looks like I'm going to have to. All right. Okay, so 2.5%. Okay, so we have a 2.5% level of significance, which is 0.025, and that gives us a Z star. The critical Z value will be equal to 1.96. Okay, you all know how to look that up. Now, the calculation of the standard error of B hat is Y, the summation Y minus Y hat squared. Okay. All right. And -2 here. So this is the calculation. We have all the numbers. Okay. The sample size was 12, and so we use the summation. I will take 2326 divided by 12 minus 1 times, and that is 11 times 25,600. And so Z is equal to 2.86. Okay.
Professor, the
Yes.
sample size is only 12. So how come we're not using a T statistic?
We have to be using a T statistic. So I mean, you get that one right. But when I'm trying to explain things to students, I try to simplify things as much as possible. But we should use a T because this is a small sample. Okay, and you're perfectly correct. Okay, you're perfectly correct. And I'm going to illustrate how you could have used a T to do this. The point of the matter is that, of course, you use n-2 degrees of freedom, so you would have been using a T at 9 degrees of freedom. And the result will not be much different, okay? But we're going to pull up a T, and you really have a big point. And I'm glad that, there's somebody in the class who understands that complication, okay? And it's very, very, I'm very glad to see that. But I try to use a Z to begin with so that at least we can understand it. And the reason that I have a small sample size here is that I wanted the table to fit on the screen, okay? Now, the calculation of standard error of B is summation y minus y hat squared. So we don't have summation y minus y hat squared. So we're going to go through that process, okay? We're going to go through that process. So I'm going to pull up the original data and calculate the summation y minus y hat squared so that you know how the summation y minus y hat squared comes, okay? In your exam, I'm going to actually give you all these results, okay, so that you can test your hypothesis much more easily. But I need also to be able to explain to students where these numbers are coming from. Because when you go out there, somebody's going to really make you bring out the numbers yourself, okay? This is number one. Number two, some of you, over the years when I've been teaching this class, some students have really gone out to do more statistics. And when you go out there to do more statistics, believe you me, they're not going to be giving you results. They're going to be making you generate your own results, okay? So once you learn where the numbers are coming from, it's part of learning. There are lots of things that you learn that are inside your psyche in a subliminal way. And you don't know when they become very useful for you, but they do become useful because you know what's going on, rather than just accepting them blindly. For example, numerous years ago, I learned Latin in school, and I still am able to articulate some of my Latin grammar. But sometimes when I see an English word that I've never seen before, the Latin comes in. Say, this is what this word means. And so I don't have to go to a dictionary. Yeah, so that's just an example. Okay. And there are other examples. So let's go and see how the summation y minus y hat squared comes. Okay, this is the data. No, that's not the data for that. So I'm going to bring up the data for sales calls. All right. Okay, so I'm going to stop this share and bring up a new share. I'm going to bring up a new file. Okay, so the question is, what is y minus y hat? Y minus y hat is your estimate of y given a particular value of x. Let me bring up the file again. Okay, so remember when we asked ourselves the question, what the question that we asked? If you make 30 sales calls, how many sales will you make? Okay. Didn't we calculate something like that somewhere here?
Yeah, probably further up.
Further up. Well, let's keep going. All right. Thank you so much. So suppose you make 30 sale calls. How many sales will you make? So the number of sales that you estimate will be 27.77. Okay, and it could be something that you can break up into small bits like 0.77, but it could also be something that you cannot break up. For example, if the size of a house is so many square feet, what would be the sales amount? Yes, you can get a fraction, but let's take this as our estimate. So your estimate of Y, the number of sales given 30 sale calls, will be 27.77. That is your Y hat right there. Y hat simply means your estimate of Y given X. Okay. All right. So let's move on and try to calculate Y minus Y hat. Okay. Before we proceed. Okay. So I'm going to stop this share and share something else. The sales regression file. Okay. Okay. So I'm going to calculate Y minus Y hat. All right. And this will be Y minus Y hat squared to the power 2. All right. So Y minus Y hat, okay, will be equal to 19.98 and 8 plus 0.2602 times X, which is D5. Okay, so that is Y minus Y hat. Okay. And see, my correct cannot be all positive numbers. Cannot be all positive numbers. Y minus Y hat. Oh, no. Excuse me, guys. I have to calculate a Y hat first. Sorry. You have to calculate Y hat first before you calculate Y minus Y hat. Okay. So Y minus Y hat is, this is actually Y hat. And then this is now Y minus Y hat. Sorry, guys, that I missed that one. So then Y minus Y hat will be equal to Y, which is C5, minus Y hat, which is J5. C equals C5 minus J5. Okay. All right. So you have some negative, some positive. All right. We'll copy that formula, put it there. And you can see that if you really do it, because I use 0.2602, if I had used 0.26026, actually, I think it's 0.2606. Let me see. I'm just trying to make sure that okay. Well, Actually, then this number should actually be 0. But like I said, I use an approximation. I use an approximation. Oh, I did not. All of this. All right, you can see that you are getting closer and closer to 0. If you use the full scale of the decimal points, this should actually come to 0. You can see it's very close to 0. And then you do y minus y hat squared, which is equal to k 5 to the power 2. Okay. And you get a summation. All right. So that is the summation y minus y hat squared. You write it down. All right. Now, the reason I say write it down is that I'm going to go back to the PowerPoint slide. Okay. So I will stop share this 587.1101. 587.1101. All right, so let us stop share this and go back to our formula. I mean, what do you call it? PowerPoint slides. Okay, so now we have the formula for the standard error of v hat. Okay, this is the calculation for the standard error of v hat. And the standard error of v hat is summation y minus y hat squared. And so the summation of y minus y hat squared, let us see if we are really looking at, this is a different problem. So I'm going to plug this in, okay? And we have, this is for the other problem. So let's look at 587.1101, 587.1101. Divided by, did we actually have a sample size of 12? Okay. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Actually, we have 15 here, not 12. 1, 2, 3, 4, 5, 6, 8, 9, 10, 11, 12, 13, 14, 15, 16. Let me be sure. Sales calls. 1, 2. Okay. Actually, we have 15. Okay, let me pull that up again. It's 15 of them. So let's look at the formula. Okay, so this is 15 minus 1 times n minus 2, should be n minus 2, not n minus 1, times summation x minus x bar squared. And what did we have? X minus x is 25,600. Okay, so let us see what we have. So can somebody get that calculation for me? Um, 25,600 times 13. Okay. Times 587.1101. Okay. And to the power 2. Is 0.0. Let's see. 600 times 13. Okay.
I'm not sure if this is right. I got 0.042.
0.042.
Yeah, 0.042001820.
I
Okay.
got the same.
All right. I'm glad to.
Yep, I got the same.
Got the same thing? Okay, 0.042. Okay, let me just make sure of my calculations.
It's supposed to be 15 minus 2, not 15 minus 1.
No, it's 15 minus 2. That was a mistake. I seem to get 0.0176. Let me do it again. Let me do it again. 13 times 25,600. Okay. Okay.
Yeah, I got the same answer again.
Okay. You're perfectly right. Ah, yes, 0.042. Okay. All right. Thank you very much. And so now we have the standard error of B hat. Remember, we would take the B hat minus 0 divided by the standard error of B hat, which is 0.042. 0.042. And so what do you get? 0.2602 over 0.042 will give you 6.195. Did you get that?
I mean, I got 6.0079.
Okay, all right. I mean, it might just be the way we put up the decimals, okay?
Yeah.
All right.
Also, you got to change the z-score on the next line to 1.9.
Yes. Yeah, the critical Z. Well, I'm testing at 0.01. Okay, testing at 0.01, but let us use what we said, 0.025, and so this becomes 1.96. You have a very valid point, 1.96, and so if Z of 6.195, 6.195 is greater than the critical Z, 1.96. So then we reject the null hypothesis that B is equal to 0. We reject the null hypothesis that calls do not significantly affect sales. Am I correct? Hello?
Yes.
So we are rejecting the null hypothesis that calls do not affect sales. Therefore, we conclude that calls significantly affect sales performance. Does it make sense now?
Yep.
Okay. All right. So now this illustrates a whole set of points here. One, we estimate the slope. We estimate the constant. We estimate the coefficient of determination, and we test the hypothesis for the slope. Okay. And somebody, asked me a question about the homework assignment and said, is this about airfare? The answer is no, because we were talking about the maintenance. Okay, does the age of the bus affect the amount of money we spend on maintenance? And so,
Oh wait, Professor, that was me who asked that question. And
okay.
I'm looking at it right now, and it says use regression analysis to identify the fixed charge
Yes,
and the cost of additional mile transportation.
Yeah, the additional mile driven for the vehicle.
But when we do the regression, like, okay, the reason why I said airfare is because we had a question similar to this in Business Statistics 1. And we had airfare against distance, which was miles.
Mm-hmm.
So
but we're looking at airfare as dependent on miles. But
correct.
This one is maintenance expense depending on how many miles you drive in the vehicle. Because if you drive a vehicle 10,000 miles a year and I drive my vehicle 25,000 miles a year, I'm going to have more maintenance expense than you. And so maybe I should change the wording of that problem to mileage driven.
No, you're right. I guess maybe I didn't look at maintenance as having like a fixed cost, but I guess you could look at it.
If you didn't drive your car at all in a year, normally you should at least change the oil every time.
You're right.
Okay. I mean, and for a company that has a fleet of vehicles, whatever happens, somebody's going to do some check on the vehicle and make sure, even if they don't drive it. Well, typically they will. I mean, and we also, if I give you a regression result from SPSS, you will see also a fixed maintenance cost. If you test the hypothesis for zero driving of that vehicle, it might actually show that the constant is zero. It might come to zero. It's like when we test the hypothesis on the size of a house and the price. The constant will usually not be zero. It will amount to the price of the land. But there are also things where you test the hypothesis for the constant, it comes to a zero, It's like, height and weight. If somebody has a zero weight, like a fetus, what you will get is zero for the constant. If you test a hypothesis, you will not be able to reject the null hypothesis that the constant is zero. And I have some examples somewhere. Okay, so that ends. These are other examples which you can test out by yourself. Dividends and the price of a share, which we talk about in finance. Okay, so you can look at that. This is the bus example. You can work it out yourself. Okay. I don't think that this is correct. I'm going to delete that. I think I had walked through it myself and found out some significant error, but I do have a correct solution, which I'm going to. Okay, this is the T value that I used there. I'm going to, and this is an incomplete solution. Okay. Okay, here is a regression using SPSS. Okay. The amount of food expenditure per family depends on the size of the family. Okay. Food expenditure in the family depends on the size of the family. And so here we have an estimate of 3.379 and 4.414, which is if the family increases by 1, and then you would have extra 41 cents spent for each increase of family by 1. Now this is an SPSS printout, and if you look at SPSS printout, which I will usually give you in a test, what you then do is you use this calculated T and compare it to a critical T. You don't have to go through all this thing that we went through. You just use this when we were in the classrooms, which I'm going to try to bring this to the classroom. I'm going to find somehow, to give you access to give students access to this SPSS that is not in the lab, so that we can actually go through how to use SPSS, because in the past, we did SPSS in this class. And by the time you leave this class, this particular intermediate level business statistics class, you would have learned how to manipulate software. Okay, because this is what's going to happen in industry. They're not going to give you Excel, believe you me. They will not give you Excel. They will give you SPSS, they give you SAS, they will give you Minitab. Most companies don't use Minitab. Minitab is more like for teaching, you know, or for people doing private practice in a small company. In big companies, they use SAS, they use SPSS, they use E-views, econometric views, because E-views is really very powerful econometric software. So is SAS, and so is SPSS. Okay, so and you use the usual methods. Yeah, go ahead.
You see the E for the error at the top, or the model Y. Which E does that represent when we're looking at the bottom? Is it the constant? Is it the slope?
No, that E here, the E is Y minus Y hat.
Oh, okay, the residual, right?
Yes.
Got it.
The E is Y minus Y hat. In a sense, what we're acknowledging here is that the 414 here is an estimate. The 3.379 is also an estimate. So you must account that there has to be an error whenever you do an estimate.
So is it like an average value error?
No, it's the error that is pertaining to a particular level
to
of
that particular value. Okay.
Yeah, to a particular value of X.
Got it. Got it.
Okay, and so you get an estimate. Now, when you sum it, that is when, remember that when you are calculating the standard error of B hat, you use that E squared for each observation.
Professor, just to add on to his question, when we run the hypothesis test, we use those two numbers at the bottom, which was 0.414, 0 minus 414 divided by 0.48.
Now, when you're doing a hypothesis test, you either take 3.39 minus 1.96 divided by the standard error of A, okay? And I didn't give you the standard, divided by this standard error, okay? 3.379 minus 0 divided by 0.196, because here it gives you the standard error right there. So if, now do it a little calculation by yourself, take 0.414 and divide it by 0.048 and see what you get. You're gonna get 8.625.
Got it. And that'll be the critical value. I mean, not the critical value, but the Z value.
The calculated Z value.
The calculated T value. All right.
Yes. Okay. So in a sense, SPSS gives you all that information. B minus 0 divided by 0.048 will give you this calculation. So if I give you an SPSS printout, you don't need to trouble yourself. You just go for that. Now, I could give you an SPSS printout and I'll take all these other things out because I want to test your ability to get that number by yourself. So you need to keep the formula in your head, or I could give you the formula. See, nowadays, way back, talking about the 1970s, or when I was in high school, when school was school, you have to memorize formulas. They never gave you formulas in those days. You had to memorize the formulas. Okay, and you can see here, we went through that process and we tested the hypothesis. And so I would expect you to be able to test a hypothesis. All right, does anybody have any other questions? All right, hearing none. Thank you all for being present. I'm going to post this on YouTube so that you can see it again and benefit from the questions that were asked. We all right?
Thank you, Professor.
All right, so enjoy your evening. And I'll see you guys next week, Tuesday. And then we're going to get into multiple regression.
Thank you, Professor.
All right, have a nice evening.
Good night.